Hello everyone, I'm Jyoti from BSc Chemistry Honors second year. So this video is specially for visually impaired students and the chapter name is Chemistry of Actinides from Inorganic Chemistry. Let's start. Actinides constitute a series of elements following actiniums in the seventh period of the periodic table. Actinides belong to F block as these are formed by the gradual filling of 5F subshell. We have discussed the chemistry of lanthanides in the previous chapter. Lanthanides which follow lanthanum involve the gradual filling of 4F subshell. In this chapter, we will discuss the chemistry of another series of 14 elements which follow actinium. The series of 14 elements is called actinides. Actinides along with lanthanides constitute complete F block elements. The ending "ide" in actinides is not appropriate because it more correctly means negative ion, such as oxide or chloride. Actinides were also named actinides by a group of scientists. However, the ending "on" is used preferably for non-metals such as boron, silicon, etc. Whereas all the actinides are distinctly metallic, IPAC has now recommended these elements to be called actinoids with the ending "oid" rather than being called actinides or actinides. However, it is unfortunate that people still call these elements by their earlier name as actinides. Before World War II, the only naturally occurring actinides, namely thorium, protactinium, um, and uranium, were known. Uranium is the heaviest naturally occurring element. It was after World War II that the remaining elements were artificially discovered through nuclear reactions. These elements are named man-made or synthetic elements. Another name coined for these elements is transuranic elements. Transuranic elements are elements that have atomic number greater than 92. Let us now discuss the interesting aspects of the chemistry of actinides. Position of actinides in the periodic table. An inspection of the periodic table reveals the electronic configuration of noble gas radon as given below. After radon, the 7s and 7p orbitals gain stability relative to F5F orbitals because S and p orbital are more penetrating than the D and F orbital. As a result, the next two electrons are being filled in the 7s orbital, which mark the appearance of new elements francium and radium belonging to S block of elements. After the addition of two electrons in the radon core, the 5 and 6d electrons penetrate the 7s orbital. The least penetrating F orbitals are stabilized on the account of the increase in effective nuclear charge outside the noble gas core with increasing atomic number. As a result, the next 14 electrons from the thorium, lawrencium. It is important to note that around actinium, both the 5F and 60 subshells possess almost similar energies. Because of similar energies of 5F and 60 subshells, the incoming electron may enter either of the two subshells, which results in the uncertainties of the electronic configuration. As a result, it is doubtful whether the electron enters the 5F orbital or not. For example, the configuration of thorium may be written as given below 5F062 7s2 or 5F161 7s2. However, once filling starts in F orbital, the 5F subshell become more and more stable. As a result, from uranium onward, the 5F shells become more stable. Thus, all incoming electrons starts filling progressively in F orbitals. The general electronic configuration of actinides can be designed as 5R in 5F1 to 1461 0 to 17 is two general characteristics of the actinides. First one is electronic configuration. As already discussed in section 5.1, the actinides involve the gradual filling of 5F subshell. The electronic configuration of the titled actinium, thus from thorium onward, the 5F subshell starts progressively filled. The general electronic configuration of the atoms of the actinides in the ground state may be written as Rn 5F 1 to 14, 60 0 to 1, 7s2. The detailed electronic configuration of all the elements is presented and in table below. The second properties that are physical properties. Some of the physical properties of the actinides are present in table 5.2 which are discussed below. Melting and boiling points. The melting and boiling points of actinides are moderately high but are lower than those of the transition elements. Um, an inspection of the table 5.2 reveals that there is no regular trend in the melting and boiling point of the non-actinides. Density. An inspection of table 5.2 reveals that the elements near uranium have very high densities Americium resembles the corresponding lanthanide europium in being less dense than its neighbors. Ionic radii and actinide contraction. The size of actinide ion decreases along the actinide series. This being because with increasing atomic number, the extra charge on the nucleus is poorly screened by the f electrons. The steady decrease in ionic with increase in atomic number is called actinide contraction. A comparison of M3 positive ion radii of actinides with those of the lanthanides reveal the actinide and lanthanide ions are very small in size. As a result, their chemical properties are also similar. The decrease in ionic size ions in case of actinides as given below. It is interesting to note that there is a decrease in the atomic radii from thorium to uranium, in increase in the most stable oxidation state from +4 to +6. In other words, the metallic bonding from the uranium may be considered to consist of M and positive ions, which a total of n electrons for atoms. After the metallic radii increases significantly again, which may be reflect the increasingly lanthanide-like protection here, which refer the oxidation state is +3 with only 3 electrons per atom available for metallic bonding. Oxidation states. The actinide elements show a greater range of oxidation states than the lanthanides, particularly in the early part of the series. The different oxidation states of the elements are shown in table. Bolt's numbers are most common oxidation states. The oxidation states shown in parentheses are unstable. The +2 oxidation state in case of actinides are very rare. Am2 positive has the electronic configuration 5f7. It is analog of Eu2 positive in the lanthanides but exists only in solid state as the fluoride. On the other hand, Cf2 positive, Es2 positive, Fm2 positive, Md2 positive exist ions in a solution. The properties of divalent actinides resembles more closely to B2 positive in group 2. The most stable second oxidation state is exhibited by nobelium and corresponds to stable 5f14 arrangement. The third oxidation state is the most common oxidation state among all the actinides. However, this is not always the most stable oxidation state in the actinides. The first four elements, that is the THP, U, and NP, do not show +3 oxidation state as the most stable oxidation state. For example, U3 positive is readily oxidized as well as in solution. Interestingly, the most stable oxidation state of elements up to uranium is the one of the involving valence electrons. Thus, the most stable oxidation states of thorium THP and U are 4, 5th, and 6th respectively. The 4 oxidation state is exhibited by all the elements from Z equals to 90 to CF Z equals to 96. However, Pa and Np displays the most important +4 oxidation state. The 5th oxidation state is exhibited by all the elements from 91 to 95. However, +5 oxidation state is most stable for Pa and Np. It is important to note that M5 positive ions do not occur in solution. The 6th oxidation state is exhibited by the lower actinides in the form of their fluorides. The 6th oxidation state is most commonly found in the dioxo ions. The ion MiO2 positive is linear and exists both the solid as well as the solution. One of the most commonly encountered compounds of uranium oxidation state is uranyl nitrate dihydrate. It also consists of linear, is surrounded by two NO3 negative ions and water molecules. The NO3 negative groups are bidentate and therefore two oxygen from each NO3 negative are bonded to radium. Oxygen atoms from the two water molecules also bound to a uranium, thus the coordination number around uranium is 8. The unit in the compound U2NO3 to which is perpendicular to a hexagon of 6 oxygen atoms, 4 from bidentate NO3 negative group and 2 from water molecules. The lower oxidation states are ionic while higher oxidation states are increasingly covalent. The 7 oxidation state is known only in oxidations of Np and Pu when alkaline solutions are oxidized by O3. Colors of the ions. Actinide ions are mostly colored. The color of particular actinide ion depends upon the number of electrons present in the 5f orbital. The color of the actinide ion arises mainly due to the FF transition. The color of the characteristic cation formed by the actinide ions in aqueous solutions. In addition to FF transitions in actinides, the color can also rise due to FD transition as well as charge transfer transition. The color of the actinide ion solution because of effect transition occur in the visible and ultraviolet regions. We have already encountered this F-type transition case of lanthanides as well as since the 5 electrons in case of actinide are projected outward more in space than 4f electrons in lanthanides. These 5f electrons are strongly influenced by the ligand field of ligands. This makes the absorption spectra of the actinides more complex compared to the straightforward spectra of lanthanide. A complex spectra is always different to characterize easily. It has been experimentally found that the absorption due to FF transitions in case of actinides are nearly 10 times stronger and 2 times broader than the F transition of lanthanide ions. The energy difference between 5 and 60 orbitals in case of actinides being smaller than 4f and 5d orbitals in case of lanthanides. The actinide ions invariably absorb light of lower frequency or higher wavelength. As a result, the lower and very strong FD transition lie in ultraviolet region and therefore do not influence the color of the actinide ions. It has been observed that the actinide ions is higher oxidation state display predominantly charge transfer spectra. The spectra is exhibited only by high oxidation state ions which can easily oxidize the ligands. It is important to note that the lanthanides do not exhibit charge transfer spectra because lanthanides do not display oxidation states higher than 4. Magnetic properties. The actinides show similar magnetic properties to lanthanides in terms of magnetic moments with the number of unpaired electrons. This is shown clearly in the figure where the magnetic moments are plotted against the number of unpaired electrons. It is important to note that the high valence state have been chosen for uh, 5f1, 5f2, 5f3 and 5f4 ions which show the close similarities. Magnetic moment values for the isoelectronic actinide ions are lower than the lanthanide ions. Reactivity. The actinides are highly reactive metals. These react with dihydroxide and form non-stoichiometric hydrides with the formula MS2 or MS3. They react with hot water and tarnish or MS3. They react with hot water and tarnish in air forming an oxide coating. Actinides react readily with HCl but reactions with other acids is slower than expected. The metals are basic and do not react with sodium hydroxide. The actinides react directly with the halogens to form a variety of halides. The redox potential for known for the M3 positive to M couples are about minus 1.91. Thorium and uranium chemistry has been exploited in detail. Some of the general methods for preparing compounds of actinides are given below. Occurrence and isolation of actinides. All the elements beyond actinium in the periodic table are radioactive. As a result, the nuclei of the actinides are unstable and undergo radioactive decay. Among the actinides, uranium is the heaviest naturally occurring element with an abundance of 2 4 in the Earth's crust portion in the Earth's crust and is more abundant in Ag energy than Ag energy. Among the actinides, TH and U occur on the Earth because the isotopes of uranium thorium have half-lives sufficiently long in view of the fact that the earth was formed several million years ago. Uranium, since uranium is the most important of all actinides, its chemistry will be discussed in more detail. Primary natural source of uranium is the pitch blende or uraninite, which has the empirical formula U3O3 is mixed with the containing uranium both in fourth and sixth oxidation states such as UO2 and 2UO3. The other important occurs such as kernite, arsenide, calcium kernite. Extraction of uranium is already mentioned. The main source of uranium is pitch blende. The details of extraction of uranium involve the following step. Concentration. The ore is crushed to fine powder is subjected to conventional gravity separation. Remove the lighter impurities. Then the roasting. The concert ore is roasted on the head of reverberatory furnace in the presence of to remove volatile impurities such as sulfur, arsenic, and antimony. Acid treatment. A roasted ore is treated with dilute H2SO4 in the presence of an oxidizing agent such as MnO2 and AgIO3. This treatment converts uranium to soluble uranium sulfate (UO2SO4). The roasted ore may be treated to solution by dissolving the ore in nitric acid. Treatment with ammonium carbonate. Addition of ammonium carbonate to the above solution. Vinyl sulfate precipitate is ammonium uranyl carbonate. Alternatively, ammonia added to the solution of uranyl sulfate obtained in step 3 that gives the rice bright yellow precipitate of ammonia diurenate. The precipitate, often called the yellow cake, the cake on heating gives rise to mixed oxide uranium um, conversion of uranium dioxide into uranium dioxide. The mixed uranium oxide is reduced to UO2 by heating the by charcoal or with hydrogen. Production of uranium elements. Uranium can be produced from uranium dioxide by using either of the methods. UO2 is heated with vapors of HF and uranium for fluoride, which is turned reacts uh, reacts with magnesium to uranium metal, or by converting UO2 to a volatile uranium tetrachloride, heating it with elemental chlorine in the sense of charcoal. All the steps detailed above can be summarized in the flow sheet diagram of extraction of uranium, chemistry of separation of neptunium, plutonium, and americium from uranium. The three elements neptunium, plutonium, americium that follow uranium in the actinide series are produced mainly from uranium in the nuclear reactors. If you recall, uranium is the oldest known element amongst the actinides. Naturally occurring uranium contains main isotopes 230 uranium, 35 uranium, which occurs in ratio 99.3 and 0.7%. There is another isotope which occurs in traces only. Neptunium and plutonium, named after the planets Neptune and Pluto, were prepared for the first time in 1940 by a team of celebrated scientists of bombarding uranium with neutrons in the cyclotron in Berkeley. Both the elements are now obtained from spent uranium fuel elements of nuclear reactors, where are formed by the capture of neutrons produced in the fission. Isotopes of plutonium Pu can also be prepared by end-to-end reaction in which a fast neutron is added with the subsequent loss of two neutrons. Americium can be obtained from the isotopes of plutonium by success and gamma reactions in the nuclear reactors, as the yields of the heavier elements after americium is controlled by two factors: the half-lives of the various isotopes by the ability of absorb neutrons. It is important to note that the stepwise addition of slow neutrons is very difficult. A quick method is to bombard the nucleus with a large number of fast neutrons without allowing time for the intermediate product to decay. For example, uranium adds a fast neutron and then allows two neutrons to form an isotope neptunium according to the reaction. The separation of these elements and ppm and am for uranium is extremely difficult and hazardous. It is because these elements, including starting material, and are not only highly reactive but also give highly reactive fission products. Plutonium, especially, is extremely toxic. A dose of small 10-6 gram may be fatal, but smaller doses are carcinogenic. The separation of NPP and AM from U are based on the following chemistry. Stability oxidation state. A steady decrease in stability of high oxidation state with increase in atomic number have been observed. With the increase in atomic number, the order of stability. The major ions involved are AM3 positive, PU3 positive, and P3 positive, E positive. A separation of these elements from uranium, from fission products, and from one another can thus be achieved by adjusting the solution containing them to suitable redox potential and then using solvent extraction for precipitation. For example, Pu can be oxidized to PuO2 negative while Am remains as Am3 positive. Thus, plutonium Pu can be removed by solvent extraction, whereas americium can be precipitated as AmFC3. Extraction into organic solvents. The MO2 positive ions from solutions can be extracted into organic solvents. The M4 positive ions are extracted into tributyl phosphate in case kerosenes from 6M HNO3 solution, where M3 positive ions are extracted from 10 to 16M HNO3 precipitation reactions. Actinides in +3 and +4 oxidation state can be precipitated as they fluorides or phosphates from acid solutions. The higher oxidation states give either no precipitate or can be prevented from precipitation by complex formation with sulfate ions. Ion exchange methods. Ion exchange methods are commonly used in separation for small amount of materials, as in the separation of MRS, MEM, spent uranium fuels Rods removed from the nuclear reactors can be used to extract NP and P is kilogram quantities, where AM is 100 gram quantities. This reprocessing of nuclear fuel rods is an important technology as this helps to extract new elements that may be used in nuclear fuel, spent fuel, or rods are dipped in ponds of water for several days to allow them to cool during this deployment period. The intensely radioactive isotopes with short half-lives such as 151 I lost most of their activity. As a result, nitrates of U2O2 positive, U4 positive are preferably extracted in tributyl phosphate, leaving the other actinides, namely NP and AM, along with other fissile products in aqueous solution. Um, U2 positive species present in kerosene oil on treatment with 0.2 NHNO3 gives U2NO3 in aqueous solution, which on evaporating leaves a solid mass of composition. On heating, this hydrate solid compound to 400 degrees Celsius gives UO3, which upon further reduction yields UO2. On the other hand, aqueous solution of a reduced PU solution on treatment with nitrous acid gas oxidized to PU. This solution reacts with oxalic acid to crystalline precipitates of the composition. Heating the hydrated compound to 300 Celsius gives PU to the whole sequence steps outlined in the process are described. The separation of other actinides, namely PNAM, can be achieved by the use of appropriate oxidation reduction cycles coupled with solvent extraction. For example, Q3 positive in aqueous nitric acid can be oxidized by an oxidizing compound. Transuranic elements, elements with an atomic number greater than 92 are called transuranic elements. Before Second World War, the elements thorium, protactinium, and uranium were located below hafnium, tantalum, and tungsten with the periodic table. The synthesis of neptunium, a new element with atomic number 93 by MC Millen and Abelson in 1940 was demonstrated by bombarding uranium with neutrons. This newly discovered element should be positioned immediately to the right of the tungsten below uranium. However, the properties of neptunium resemble more with the uranium rather than the uranium. It was discovery of Neptunium followed by the subsequent synthesis of new elements that were for the new series of elements called actinide series. All the transuranic elements are radioactive nature and have short life period. However, the elements were later found to be present in trace quantities in uranium ore such as neptunium, plutonium, and americium. Synthesis routes to transuranic elements. There are two synthetic routes which are commonly used for synthesis of transuranic elements. A neutron may be captured by the nucleus, neutron may be captured by the nucleus with the emission of gamma rays and gamma reaction. The neutron increases the mass number of the nucleus by 1 of unit and some energy of release at gamma radiation. Further, this makes further nutrition may be added a similar way. Addition of neutrons increases the neutron to proton ratio. This makes the nucleus unstable because it contains too many neutrons. As a result, the nuclei decay by converting neutron into proton particle. This reduces the NP ratio, also increases the atomic number by 1. The other method involves the capture of small ions by the heavy nucleus. This is possible only if the bombarding particles have sufficient energy to overcome the Coulombic repulsions between the ionic and the heavy nucleus. The smaller are the accelerated in linear accelerator or cyclotron to possess sufficient kinetic energy. The simplest ion used in the alpha particle. This increases the atomic mass unit by several units and aromatic numbers by 2 units. Synthesis of synthesis of transuranic elements. All the transuranic elements have been prepared by nuclear reactions which involve bombardment with either the neutrons, alpha particles, or other small nuclei. It was preparation of neptunium. It was prepared by Similon and Abelson in 1940 at Berkeley by bombarding uranium 238 with slow neutrons when uranium 239 was obtained. Uh, Preparation of plutonium. It was discovered by Skarbog and his co-workers during the beta decay of neptunium. Plutonium was named after the name of the planet Pluto. Preparation of americium. Americium was synthesized by bombarding uranium 238 with alpha particle. Uh, Preparation of curium. Curium was synthesized by bombarding uranium-230 U-239 with alpha particle. Preparation of berkelium was synthesized by Seiberg and is covered by bombarding americium-241 with high-speed alpha particles. Preparation of californium was synthesized by bombarding cerium with alpha particles. Preparation of Einsteinium was synthesized by bombarding uranium-238 nucleus with accelerated nitrogen nuclide. Two isotopes of californium has been identified. Uh, Preparation of fermium. Fermium was synthesized by bombarding Einsteinium-253 with neutrons. Preparation of mendelevium. Mendelevium was synthesized by bombarding Einsteinium-253 with alpha particles. Preparation of Nobelium was synthesized by bombarding cerium-246 with accelerated stripped carbon. Preparation of Lawrencium. Lawrencium was synthesized by bombarding chloroformium, californium 250 with accelerated boron nuclei. The latter or heavier actinide elements, the elements from curium onward, namely curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, and lawrencium. Nameless later actinides. Very little is known about the chemistry of these later actinides because of their limited availability and extreme instability. The availability of some of the most accessible isotopes are given below. It is clear from the table that curium is available only in microscopic quantities, whereas the later actinides above atomic number 100 will be prepared by only in minute quantities. In other words, the actinides are available in trace amounts. It is interesting to note that later actinides show close resemblance to the lanthanides. However, the actinides can be easily separated from the lanthanides because the actinides readily form complexes for ions are absorbed on cation exchange column. The actinides can be from the column. The actinides can be related more conventionally with concentrated HCl. After relating the actinides can be separated with the from each other by an exchange using treated solutions of them. It is in order in which the tripositive ions are related shows a close similarity to the order in which the tripositive lanthanide ions are related. Displays the dilution diagram of the actinides and lanthanides elements. The first identification of elements from americium to mendelevium on a variable scale was made through illusion. All actinides, atomic number 9061 and 3 cm, VKCFE, SFMMD, no WD with exponents +1. This because it's the most favorable F14 electronic configuration. Actinides with atomic number 92 1 and 2, that is californium, nobelium, also display plus second oxidation state except for nobelium plus oxidation state is strongly reducing in nature. Similarly, berkelium compounds are less stable in plus 4 oxidation state and such as BKO2 and CS2BKCl6. Another enzyme is stony plus 3 oxidation state and act resist oxidation and reduction. This resistance to oxidation and reduction illustrates the stability of F4 F14 uh, electronic configuration. The element up to atomic number 100 undergo radioactivity mainly by emitting alpha particles, beta particles. The latter elements become increasingly unstable as the atomic number increases. Nobelium terminally is unstable and has a half-life only 3 seconds. The the actinide series is incomplete. The actinide series is incomplete at where we were Lawrencium. We have already learned that the half-lives of the later actinides beyond atomic number and decreases considerably. For example, the half-life of nobelium is only 3 seconds. It has been calculated the half-life of the elements of will decrease the half-life of the elements will decrease Further, as new elements are discovered, the half-life of an element with an atomic number 100 is expected to be very short, about 10 to 4, 10 to 6 seconds due to spontaneous decay. As a result, it is extremely difficult to synthesize and study the chemistry of elements beyond 108. However, these difficulties have not dampened the spirit of the scientists, and they have been successful in discovering elements up to atomic number 12. Out of 120 elements up to atomic number 109, we have so far been named. A major controversy came to light over naming these elements. The choice of the name of the element belongs to the discoverer. Its case of Actinides, three nuclear facilities are in competition for the synthesis of each of now newly discovered elements. The facilities are at Berkeley, California, Dubna, and Darmstadt. It is extremely difficult to identify which nuclear facility and the true chain. For example, the discovery of element 104 was claimed by the Berkeley and Dubna. The Americans named the element Rutherfordium, while the Russians named it Kochtovium. While these conflicting claims were being settled, the International Union of Pure Applied Chemistry devised hybrid Latin Greek numerical system of providing provisional names and symbols to all the newly discovered elements. In some cases, the names are shortened by removing the repetitive letter. Is that BIIM can be written as BVM, or trium can be written as short as trium. That is an element with atomic number 106 according to Latin Greek nomenclature. The nomenclature is derived by combining together the roots in order of digits. Comparison of actinides and lanthanides. Both lanthanides and actinides constitute elements of F block, as these involve the gradual filling of F orbitals. These elements occupy a distinct safe place in the bottom of the periodic table. They show close resemblance in the some of their properties, but also differ in many properties. Let us review some of the important points of the similarities between the difference between and lanthanoids and actinoids. Point of similarities: both lanthanide and actinides involve the filling of F orbitals. Both the lanthanide and actinides are displayed predominantly place 3 oxidation state in the most of their compounds due to poor shielding of 4f and 5m electrons. Both lanthanide and show gradually contraction in size of their atoms with the increase in atomic number, known as lanthanide and actinide contraction respectively. Elements of lanthanides and actinides with the same number of unpaired electrons ripple similarly absorption spectra due to FF transitions. Lanthanides and actinides are electropositive and very reactive. Nitrate sulfates and perchlorates of trivalent lanthanoids and actinoids are soluble in water. Hydroxides, fluorides are carbonates of trivalent lanthanides and actinides. Both lanthanides and actinides can be separated by ion exchange method. Ion exchange method. Points of differences. The important points of differences between the lanthanides and actinides are presented below. Here the table is given. Metal orbitals. Lanthanide involves filling of 4 orbitals. For actinides, it involves 5 f orbitals. Energy gap between f and d orbital. The energy gap between 5f and 4d and 5d and 4f orbital are higher in lanthanides. Binding energy of 5f orbitals are less in lanthanides. Oxidation states. The most commonly oxidation state is the +3 oxidation state of lanthanides, +2 +4. The common oxidation state in addition to the some actinides showing +4 +5 +6. Shielding effect. 4f electrons exert greater shielding effect. 5 electron negative 4 shielding ability to form oxocations. Lanthanides do not form oxocations. Actinides form octonides. Oxidation states. Color of the ions. Most of the lanthanide ions are colorless. Most of the actinides are colored. Complexing ability. The tendency to form complex is small. The tendency to form complex is large. They do form complex by hiding bonding point. Radioactivity, all lanthanides except brominium are not radioactivity. Coordination number lanthanides display coordination number 6, 7, 8, 9. Lanthanides display here counter number 8, 9, 12. Uh, Compounds of lanthanides are less basic in character. Compound. uh, Less basic in character. Compounds of actinides are more basic in character. Thanks for watching.